made it. Another week down. On to the next, and Super Bowl Sunday coming up. Is everyone excited for Patriots? Or is anyone a West Coast? Are you a Seahawks?
I just don't like Patriots.
Just don't like Patriots. You're going to say that out loud, like we're live right now. People, they can't see you, but they'll find you, the Patriots fans. They're not as vindictive as Eagles fans. I went to school in Philly. Philly, they'll get you. A friend lost a tooth when someone hit him with a beer can because they thought he was like deliberately cursing the Eagles, like he was wearing a Santa suit. And do you know the Santa suit for the Eagles? This is important. These are the lessons that you come to college for. So the Eagles, Philadelphia Eagles, years ago, they were in the playoffs. It was snowing. And there was someone dressed as Santa in the crowd. Eagles they were doing well, like something was happening, but then people started pelting Santa with snowballs, and they thought it was funny, so more people started pelting them. And Philly fans get pretty rowdy, so they're just like, anyone in a Santa suit is now getting hit with snow. And then for the next 20 years, they would get to the playoff. They would either not make the playoffs or get there but always lose. They could never make it to the Super Bowl. And it was Santa's curse. So they were convinced that Santa cursed the Eagles so they could never win the playoffs and get into the Super Bowl. So if you show up in a Santa suit at Eagle Stadium, best case is you get booed out and they just send you home. Worst case is someone throws a beer can at you and you lose a tooth, and then you go to emergency room. That's the Eagles. That's my team. Anyway, that's why you come to college. All the good lessons. There was a great question. We were talking at the end of class, like post lecture, of like, why not use energy, like conservation of energy? Was anyone else thinking about this while we were doing differential equations? Yeah? No one said anything? You're just like emperor walking around naked and you're like, oh yeah, I totally love the new outfit, man. Like, what does energy method give you? Like, end of the day, what function do you get? Is that too abstract of a question? Too abstract. Okay. What is the definition of work? Is that more? Like, how do you do mechanical work? Do you remember that one? That one's less abstract. I know it's still broad. Yeah. Force and distance. So as you push something with a given force through a given distance, now you've done work on it. So in general, work energy is always describing like forces and distance. It's never a function of time. It's always distance and velocity. So the functions that we get from it would be like, what is velocity as a function of position? It's not that that's not maybe that is the information that we want, but it's never going to tell you like, how long did it take to stop this object? It'll tell you when the object stopped, like at what point, like what distance, but not at what time. But anyway, if we kind of take a look at that, if we think of this as like our initial energy of like before the block comes down and hits the spring, O for original, OG, I don't know, the original energy, something up there. It's always O, like a 0 or something. Then at any point along here, so we've got mg 0.5 equals 1/2 mv of, and again, this is like some v of x squared plus 1/2 kx squared plus mg x. And I say it's like a function of x because there is no time here. Like work is not, technically you can have work done over time, like if you're inputting power into a system, like a motor that's running at 50 watts, then you could say 50 watts times time is total energy put in, but most of the time potential energy is all position and then kinetic is all velocity. So we could rearrange this and say v squared is 1/2 kx squared plus mgx minus mg times that 0.5. So then we end up with like some kind of square root sort of equation for what is velocity as a function of position. It could be helpful. Maybe that's all you were looking for. I don't know. What do you think? One reason is that physics, like engineering, or applied mechanics 2 textbooks don't get to work energy methods until the end of the class. And so you haven't used this. It hasn't been introduced, so it's not the first thing that is taught. But I feel like you've worked with energy enough where like it kind of makes sense to go through and look at like work energy kind of formulation like this. Yeah, I don't know. It does get some weird results of, because now we have like a parabolic equation, the square root of a parabolic equation, so it's a little hard to solve things. Not impossible, just we don't really know what the range of x is to start. We can solve, I guess we could plug v equals 0 in and figure out what is max x, and that would help. Then we can find like what is minimum x. But I like that approach. Everything leads back to same equations though. Like if you're saying 1/2 mv squared plus 1/2 kx squared equals constant, it's still gonna give you the same equations. Do you know how that would, do you know why these are the same? It's not like a test, but are they the same or are they completely different? Yeah. Ooh, yeah, a derivative of the other. Yeah, if we take a derivative here, we end up with 2 times mv, 2 times 1/2 mv, times what? Chain rule. I'm just gonna randomly yell out. Well, it's not random. It's usually when I'm applying the chain rule, but it'll feel random for a while. Chain rule. Derivative of v is a, yeah. And then here we have 2 times kx, 2 times 1/2 times kx, times what? Chain rule. V, yep. Derivative of a constant, 0. It would be pretty boring if V was always 0 in this equation. So let's find the solutions where V is not 0. It's the exact same thing, like whether you use work energy or free body diagram, kinetic diagram, end up in the same place. Kind of cool. This one, this is called like the Hamiltonian, not connected to Hamilton the musical, connected to Hamilton the physicist. Different, much less, like, I mean, probably an interesting person, but probably much less entertaining than Hamilton the musical. But Hamiltonian, add the energy, Lagrangian, subtract the energy. Same thing, still a constant. It's, yeah, you get different equations, but anyway. Okay, it seems like we've done enough based on the vibe that I'm sort of feeling. So let's try it again. Rinse, wash, repeat. Part B. Let's look at this one. Here, there were some different ideas of like what the free body diagram looks like. Let's start with just a couple of forces to start, and if you want to add more, you can always add other things afterwards. I like to start simple and then go from there. So we had some kind of like viscous damping. We had the weight of the object, and then all that was going to be equal to that mass times acceleration. Here, that viscous damping, because it's viscous and we know, and we're kind of given one big parameter, it's just B times V, so some constant times how fast it goes. So what I want to go from here is first, step 1, what is the equation of motion? Step 2, solve with x0 equals 0, v0. 3.1 is like our initial speed when it hits our stopper, and then 0 is like when it first reaches, just calling the top 0 and the depth as positive depth. And I'm taking different ideas and like ignoring some of them just to try like a consistent one. So what do you think? First step, equation of motion. What is it? What does it look like? Did anyone write something down, or is yeah? Some wrote something down. Yeah. You don't have to tell me what it is. Something. Okay. This one, I just did a quick sort of. I didn't ask every single person. See like, what was your preparedness level for this class, and do you remember all of your prerequisites? It was just like a general sort of like, what do you think? Where are you at? So equation of motion. I think a lot of people, the first thing they think of are those kinematic equations of motion, where x is some known function of time, v is a function of time, and then acceleration, technically it's a function of time, it's just a constant. Like, so a is constant, and then you can find the rest. That's really like our step 2, because that's the solution to some equation of motion. So a lot of times physics sort of skips over that step because it's not trying to get you to differential equations, it's just trying to introduce things that you can solve and understand physics. I think it's a good approach, but here, equation of motion is like A is some function of position, of velocity, and time. Usually acceleration is not a function of acceleration, right? Like you don't need to know the acceleration to calculate acceleration. But if you know its position, so like if it's connected to a spring or if it's in a magnetic field, if you know where it is, you know what forces are acting, you know how big the forces are. And then velocity is the other part. Like if you know how fast it's moving, then usually there are some forces that are proportional to speed. Like this one, like viscous damping. That one's B times V. So that's what we're looking for the equation of motion. So how do we get there? How do we get there from here? Go by the Dunkin' Donuts, and then follow this, come around here. Every time F equals ma, and then solve for A. Sound good? Try that. Is that what people already wrote, if you did write something? Yeah? Nice. What did you write? Like this? It'll catch up in a second. I know, there's like... Oh yeah? I keep forgetting about that one. All right. What do we think? Give it a shot. I know it's not like a lot of math. It's not like we're going through a whole bunch of stuff. Give it a shot. What do you think? Look at our free body diagram. Pluses, minuses, like what's going where? What did you write down? Same thing?
Yeah, I'm just looking through how we got there.
Okay. You got steam cool. Okay. Yeah, like where that. I'm gonna do one thing. You can tell me if I'm wrong. Boop, doop, doop, bop. You'll catch up in a second. What do we think about that? Why would I do that? Yeah.
Because during our free body diagram, we noted that MA, that down direction is positive.
So that kinetic diagram, and again, in statics, you can kind of make a guess and it all comes out in the wash of just like, oh, turns out R was negative, so when I wrote it to the left, it's actually to the right. It becomes a lot more important to keep track. You can change you can choose whatever direction you want. Like, you're the engineer, you can choose a coordinate system. I don't want to like tell you what coordinate system has to be in your life. If you identify with a different type of coordinate system, that's okay. But you do have to be consistent that if I'm saying MA down is positive, then that like pointing up FD is a negative FD. If we flip it around and say this is an MA, then really FD and MG have to be pointing in the same direction. Kind of makes sense? Similar to the spring. It would be weird to push on a spring, and the more you push it, the more it accelerates you away. It would be weird to drop into a fluid, and the faster you move through the fluid, the more acceleration you have. It would be nice if you find a fluid like that, tell me about it. We can that is very patentable, but it's hard to come by. Okay, cool. That was the hard part. Not really. I don't know. I guess they're both hard. That's like the hard conceptual part. Identify what forces are there, and then come up with that differential equation. Next part, as you get used to it, it becomes easier, or you give up completely and you just learn how to code, and you just always plug it into code. Whatever you want to do. But here we're trying to come up with like some graphs to justify or use a decision. So let's do this. We have dx squared dt squared plus b over m dx. Oh wait, I like the dots, and I already introduced the dots, right? So x double dot plus b over m. X dot is g. I'm gonna set this up a little bit, especially since we don't have. There's no expectation that you've like mastered differential equations, and even if you've taken the class, you got the A, you've mastered it. It's probably not like the first thing you think about every morning. Like, oh man, I can't wait to separate things into homogeneous and particular solutions today. So that's okay. General process is create a homogeneous. That's sort of like what would happen if there's no external forces, like no gravity. Then the other part is a particular kind of forced solution, like what happens if there's only gravity, or gravity is kind of the main thing happening. So both of these have some function that should work. So you can start with either one, or if you have, yeah. But that's the next step, is like what kind of function would solve that homogeneous and what kind would solve that particular. Both, it'll be some kind of like function of time, right? Last time we said it was sines and cosines. This time sines and cosines aren't going to work. Like we can't add the derivative of cosine to sine, or sorry, derivative of cosine is sine. We can't add a sine to a cosine, add up to 0, so it's got to be something else. What do you think? No thinking. It's Friday afternoon. Yeah. All right. Yeah. It happens. Yeah. E to the t. Yeah. Would e to the t work? Maybe. Yeah. So if we have like t e to the t, it would start at 1 and like go up. That would be true for that case that if we had said that it was like negative b over m x dot. That the faster you move, the more acceleration you have, right? Like either negative something like that. Like an e to the negative t. Start somewhere, drop down. Never gets exactly there, but it gets close enough for engineers. By the time you hit a few time constants, you're there. Maybe an e to the negative t. Would that work? Still thinking about it. So this one, it should be like the function that we plug in for xh. If we take two derivatives and add it to its first derivative, it should always be 0.
Okay.
That's kind of what we need to do. So now it's the same thing that we did before, because if we took two derivatives of like a sine, we get a negative sign. So if we add those two together, sine plus negative sign, we get 0. That's why like e to the t kind of makes sense. let's start off. So one idea for this forced one was xp is some kind of like, I'm going to call it p instead of a. Oh, yeah. pt plus b. Where I take one derivative of it, it becomes p, and then take two derivatives of it, and then that second derivative is now 0. So I could say b over m times p equals g. P equals mg over b. Something like that. Little b, not big B. Big B is some other constant. How does that look for that particular solution? Does it solve the problem? Does it solve like that particular response? I know, it is Friday afternoon on a Super Bowl weekend. It's hard to think through engineering problems. A yay or nay? What do we think? Yay? A yay? Yay? Yeah. Not all at once. Whoa, I can't keep track. Okay. So at least in terms of like, if this thing is not accelerating, so if we have no changes in momentum, then we know our velocity is going to be like constant. That's what this particular solution would tell us. Do you see why I'm saying that? Because we basically just said like, okay, this particular solution is a kinematic, like that kinematic equation of some velocity times time, where my velocity is mg over b. Weight over that kind of drag force. So it seems to make sense. Like intuitively, it kind of makes sense that if there's no buoyancy, you'll just float down through the water at a constant speed, some kind of like terminal velocity. At least I think that makes sense. Maybe you're like, no, that's not. It's not how fluids work. You're not a fluid mechanician. I'm like, I'm not, but you know, I've jumped in a pool. Okay, so then let's try. I'm going to try this one as a throwback to probably, if you've taken DiffEq, this might be a throwback to like, oh man, I remember already some like nods, AE to the ST. Yeah, a little bit. Laplace transform comes up, everyone's favorite. What is the derivative of AE to the ST? S is constant, A is constant. I don't know what the constants are, but I know that in my function, I'm telling you they're constant. Yeah. Oh, an AT. AT? Oh, wait, no, AS. Okay, yep. Cool. All right, so then what is the second derivative? Add an extra S. ASS e to the ST. Real asshat kind of problem. We'll do a squared. Now this looks, again, like if you're thinking of like, but in differential equations we use Laplace transforms. This is a Laplace transform. Like, we're just not going through the proof of saying like, oh, we can create these tables of Laplace transforms and blah blah blah. And so when I plug this in, I get my ass times e to the st plus b over m as e to the st is all equal to 0. Again, it would be pretty boring if I just solve for the solution when e to the st is always 0, so that one's gone. It'd be pretty boring if a was 0, so that one is also gone. S squared plus b over m equals 0. Pretty sure I did that right? Oh, b over m s. Yeah, I'm like, what? I'm missing something. There we go. S equals 0. All right. I knew I was missing. I'm like, that can't be right. But how does that look? Did I break any laws of physics yet? That's the main goal, not break the laws of physics. Trying to adhere to laws of physics, at least the laws that we set up. We're the ones who define them. We're the ones who said F equals MA. This is all our own doing. You can always just say F is not MA. None of this is true. But you already agreed. You agreed to play the game. It's like you already sat down for Monopoly. You can't just start playing communism. Now we have two solutions for S. What are the two solutions? I know this is now I'm asking you to do algebra. It's like, for God's sakes, man, these are too many classes. It's too many things to remember. But this one we know, right? Yeah? You got it. No? It's okay. I thought you were raising hand. A 0 and a negative b over m. So one of them is e to the 0t, so just some constant. One of them is e to the negative b over m times t. Those are our two kind of solutions. Really, we could have done this same thing for that sines and cosines, but we would have ended up with imaginary numbers, and then we have to plug in e to the I omega t and then convert that to sines and cosines. It's not the end of the world, but it's just, I don't know. Not everyone likes imaginary numbers. My son, my 7-year-old, was like, I rocked his world when I said there were imaginary numbers. He's like, what do you mean? And I'm like, well, you know the number line? He's like, yeah. And like, you can rotate it by 90 degrees by looking at the square root of -1. He's like, what is the square root of -1? And like, it's I. It's like just a number that we call imaginary. He's like, what? Just like, it was as if he could like see in 3 dimensions, like Neo at the end of the first Matrix. But anyway, I like imaginary numbers. Not everybody likes them. They get a bad rap. Because it's called, the class is called complex algebra, right? But it's not that complex. It's just like one extra number line. And it's like, it's not that big a deal. It's more fun that way, extra number lines. E to the 0 is just going to be something, some constant. So we'll just say A plus B. So we'll have some kind of exponential decay for velocity. and then for our position, it'll like hit some like constant kind of value, something like that. At least the and then what was our particular? MGT. I called it B twice. Really, it's two different B's, but a constant plus a constant is just some other constant. So I don't really need to figure out like which one is which and how to keep track of it, because I'm just trying to figure out what is that final equation anyway. Last step, plug in initial conditions. We have two unknown things. What is A and what is B? And then we have two initial conditions. What is our initial position, initial velocity? General class of problem is that this is an initial value problem. You know something about how it started, so you're trying to predict what happens next. And again, that's sort of our implicit dogma of physics, is that if you know where something is and how fast it's moving at any point in time, you can predict it forever. Whether or not you believe that, I don't know, but in this case, in our tiny little world, that is the case. Are we out of time? Oh yeah, we're out of time? No. 1:15 start. Yeah, we are out of time. We're out of time. Okay. Enjoy the Super Bowl. Have a good weekend, and then we'll come back, pick up, and try something new.